Hello friends, welcome back to my YouTube channel. In this class I am going to discuss three more problems of chapter 6 of P.K.NAG Engineering Thermodynamics, that is 6.14, 6.15 and 6.16. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. The question number 6.14 is like this. A reversible engine operates between temperatures T1 and T. T1 is of course greater than T. The energy rejected from this engine is received by a second reversible engine which is at the same temperature T. That means the energy rejected by the first engine is received by the second reversible engine. Whatever energy is rejected by first engine is supplied to second engine, and that heat interaction takes place at a temperature T. The second engine rejects energy at a temperature T2, where T2 is less than obviously T1. So that temperature T is the arithmetic mean of temperatures T1 and T2 if the engines produce the same amount of work output. And temperature T is the geometric mean of temperatures T1 and T2 if the engines have the same cycle efficiencies. If the efficiency of these two reversible Carnot heat engines which are in series, when this thing happens, we say that two reversible engines are operating in series. And the first bit we are to prove that the intermediate temperature T is the arithmetic mean of temperatures T1 and T2 if the engines produce the same amount of work output. And if the efficiencies of the two engines in series are same, then temperature T is the geometric mean of T1 and T2. So there are two reversible engines operating in series. So let Q1 be the heat given to first engine. Suppose this is engine 1, and work output of this particular heat engine is W1. Of course, all these engines are reversible. And let Q2 is the heat rejected by the heat engine. W1 is the net work output. Out of the heat supplied Q1, W1 is the work produced and Q2 is the heat rejected, and which is rejected to the second engine at temperature T. And this Q2 is the energy rejected by the first engine, and that Q2 goes to the second engine as heat input. This becomes the input for second engine. So this means this engine and this engine are in series. And let W2 be the work output of this second engine. And let this Q3 is the heat rejected by the second engine to the low temperature T2. So first bit we have to prove that if the work produced by these two engines are same, then the temperature T is the arithmetic mean of temperatures T1 and T2. So we know that efficiency of engine 1 is equal to W1 divided by Q1, because we know that efficiency is work output divided by heat input. So efficiency of engine 1 is nothing but W1 by Q1 here, because here W1 is the work output, Q1 is the heat input. Similarly, that means work output of first engine is, this is suppose equation 1. That means work output of the first engine is the product of its efficiency and the heat supplied to it. And for the second engine, the efficiency suppose is net work output by heat input. For second engine, net work output is W2 and heat input is Q2. So efficiency of second engine is W2 divided by Q2. From that, this is true, this second equation. So since in the first case it is given that work output of both these two engines are same, work output of both the two engines in series are same. So if W1 is equal to W2, if W1 equal to W2, what I can say is by these two equations, efficiency of engine 1 multiplied by Q1 is equal to efficiency of engine 2 multiplied by Q2 from equations 1 and 2. Since it is given that work output of two engines operating in series are same, then this relation holds good. Now we know that efficiency of any reversible heat engine is 1 minus sink temperature expressed in Kelvin divided by source temperature expressed in Kelvin. So efficiency of engine 1 is nothing but 1 minus, this case for engine 1 the sink temperature is T and source temperature is T1. So I can write 1 minus T divided by T1. Similarly, efficiency of engine 2 is nothing but 1 minus, for engine 2 sink temperature is T2 and source temperature is T. So 1 minus T2 divided by T. T2 divided by T. So now by substituting the values of efficiency 1 and efficiency 2 in this equation number 3, I get 1 minus T by T1 multiplied by Q1 is equal to 1 minus T2 upon T multiplied by Q2. So this is suppose equation 4. So now I can write this equation 4 by rearranging Q2 by bringing Q2 to this side. I can write like this: 1 minus T upon T1 multiplied by Q1 divided by Q2 equal to 1 minus T2 upon T. So this is the relation: 1 minus T upon T1 multiplied by Q1 by Q2 is equal to 1 minus T2 by T. Since Q1 upon T1 is equal to Q2 upon T, you see, for heat engine 1, for reversible heat engine 1, according to thermodynamic temperature scale, Q1 by T1 is equal to Q2 by T. And this Q2 by T is also same as Q3 by T2. But from this heat engine 1, Q1 by T1 is equal to Q2 by T. So I can write Q1 upon Q2 is equal to T1 upon T. By substituting, suppose this is equation 4. This is equation 4. 4 dash suppose. By substituting value of Q1 by Q2 in equation, we get 1 minus T upon T1. What I am trying to do is express q1 by q2 in terms of T temperature only. So that we have to prove that the intermediate temperature T is the arithmetic mean of T1 and T2. So I can substitute for q1 by q2 in terms of temperatures only. So 1 minus T by T1 multiplied by T1 upon T is equal to 1 minus T2 upon T, or T1 minus T divided by T1 multiplied by T1 upon T is equal to 1 minus T2 upon T. This cancels out, or T1 minus T upon T is equal to T minus T2 upon T. So by cancelling T from both the denominator, we can get T1 minus T is equal to T minus T2. From this, by bringing T to one side, so now T becomes the arithmetic mean of two temperatures T1 and T2, because we proved that T is equal to T1 plus T2 whole divided by 2. That means the intermediate temperature T is the arithmetic mean of temperatures T1 and T2. So when work output of two reversible heat engines in series are same, then we can prove that the intermediate temperature is the arithmetic mean of two temperatures T1 and T2 only. So next bit is, this was in the first bit A, temperature T is the arithmetic mean of temperatures T1 and T2 if the engines produce the same amount of work output, that we proved. And second bit is, temperature T is the geometric mean of temperatures T1 and T2 if the engines have the same cycle efficiency. So if the engines have same cycle efficiencies, that means if efficiency of 1 is equal to efficiency of 2, that means 1 minus, you see, efficiency of 1 is 1 minus T upon T1, and efficiency of 2 is 1 minus T2 upon T, because T is the sink temperature for first engine and T1 is the source temperature for first engine. So 1 minus efficiency of any reversible heat engine is 1 minus T upon T1. So 1 minus sink temperature expressed in Kelvin divided by source temperature expressed in Kelvin. So for this engine 1, efficiency will be 1 minus T upon T1, and for engine 2 efficiency will be 1 minus T2 upon T. So that's why efficiency 1 is equal to efficiency 2 means 1 minus T upon T1 is equal to 1 minus T2 upon T. From this, I can write T upon T1 is equal to T2 upon T. On cross multiplication, we get T square is equal to T1 multiplied by T2. So T is equal to square root of T1 T2. So that means this intermediate temperature is the geometric mean of two temperatures T1 and T2. So that's what we have to prove. So when the efficiency of two reversible heat engines operating in series are same, then the intermediate temperature is the geometric mean of two extreme temperatures. So temperature T is the geometric mean of temperatures T1 and T2 if the engines have the same cycle efficiencies. So that's what we are required to prove, and we just proved it. So question number 6.1, 6.15. Question number 6.15. So question is like this, and this question is actually based on whatever results we got in the previous question. So you see, two two Carnot engines A and B are connected in series. Obviously Carnot engines means reversible engines. A and B are connected in series between two thermal reservoirs maintained at 1000 Kelvin and 100 Kelvin. These are two extreme temperatures, T1 and T2, as it was in the previous example. So engine A receives 1680 kilojoule of heat from the high temperature reservoir and rejects heat to the Carnot engine B. Obviously, when two reversibility engines are operating in series, the energy rejected by the first engine goes as energy supplied to the second engine. The engine B takes in heat rejected by engine A and rejects heat to the low temperature reservoir. Low temperature reservoir here is at temperature 100 Kelvin. So if the engines A and B have equal thermal efficiencies, determine the heat rejected by the engine B, temperature at which heat is rejected by engine A, and the work done during the process by engines A and B respectively. So there are two cases. First case is for work same thermal efficiencies, and second case is if the engines A and B deliver equal work, then determine these things. So for the first bit, we have to consider that the efficiencies of the two Carnot heat engines operating in series are same. So suppose these two engines are A and B, the highest temperature is 1000 Kelvin, and this heat is suppose Q1 is 1680 kilojoule. It's supplied to the engine A, and it is supplied at 1000 Kelvin temperatures. So this is suppose WA is the work output of engine A. The intermediate temperature is suppose T, at which the heat engine heat is rejected by this heat engine, and at the same temperature heat is supplied to the second engine, that is B, and the same energy. Here whatever energy is rejected by the first engine, that is also the same as the energy supplied to the second engine B. So this is the basic concept behind the reversible engine operating in series. Let WB be the work output. If the engines A and B have thermal efficiencies, then we have to determine some questions. We have to find out answers to some questions, or we have to find out some values. So first of all, if we just solved a question that when the efficiencies of two heat engines are equal, then this intermediate temperature is the geometric mean of the other two extreme temperatures. That's what we just proved it. So you see, in the first bit it has been asked, determine the heat rejected by engine B. Determine the heat rejected by engine B. That can be determined. You see, both these heat engines are reversible. So Q1 by this temperature is equal to Q1 by 1000 Kelvin is equal to Q2 by T, and this is again equal to Q3 by 100. Q1 is given, that means 1680 divided by 1000, this is kilojoule and this is Kelvin. These two values are not known to us, so I can equate this and this Q3 so that I can obtain Q3. Q3 is equal to 1680 multiplied by 100 divided by 1000 kilojoule, and this is equal to 168 kilojoule. 168 kilojoule. So whatever has been asked in the first bit, you see, determine the heat rejected by engine B. Engine B. And here the answer is 168 kilojoule. 168 kilojoule. And in the bit B, you are required to find out the temperature at which heat is rejected by engine A. The temperature at which heat is rejected by engine A. That means we have to find out the intermediate temperature. That this temperature we are required to find out. And you see, it is given that the efficiencies of two reversible heat engines are same. So when the efficiency of two reversible heat engines operating in series are same, the intermediate temperature is the geometric mean of two temperatures. So directly I can use that, or you see, we know that efficiency of first engine is 1 minus T upon 1000 is equal to efficiency of second engine is 1 minus 100 upon T. 100 upon T. You see, this temperature is 100 and this is 1000. So for the first engine A, efficiency, since it is a reversible heat engine or Carnot heat engine, 1 minus sink temperature divided by source temperature. And for second Carnot engine, 1 minus 100 by T. So on equating this, I can get square root of and that is equal to 316.3 Kelvin. This temperature is the intermediate temperature, or the temperature at which heat is rejected by engine A. And in the bit C, we are required to find out the work done during the process by engines A and B. You see, in the bit C, the work done during the process by engines A and B. So WA and WB we are to find out. For finding WA, we have already got Q1. Q1 is given. If I can find out Q2, then I will be able to find out WA. And Q3 has already been calculated. So if I can find out Q2, all my questions will be solved. So we have to find out Q2. We know that Q1 by 1000 is equal to Q2 by this is intermediate temperature 316.3. Q1 is 1680 divided by 1000 is equal to Q2 divided by 316.3. This is kilojoule in terms of kilojoule, this is Kelvin. From this, Q2 is equal to 1680 multiplied by, here it comes Q1 by 1000 is equal to Q2 by this T. T is just 316.3. So this is and this is equal to 531.26 kilojoule. Then WA is equal to Q1 minus Q2. You see, work output of engine A is Q1 minus Q2. this is equal to 1680 minus 531.26 kilojoule. This is equal to 1148.74 kilojoule. Similarly, for WB, work output of engine B will be Q2 minus Q3. Q2 minus Q3. So this is equal to Q2 minus Q3. This is equal to 531.26 minus 168 is equal to 363.26 kilojoule. So when the efficiencies of two Carnot engines operating in series are same, these are the values that are required to be found out. So for next bit, when the work output of these two engines are same, work output of two engines are same. So I have to find out answers. Work output of two engines are same. You see, work output of two engines are same. You see, if engines A and B deliver equal work, determine the amount of heat taken in by engine B and the efficiencies of engines A and B. So in the same diagram, suppose this is 1000 Kelvin and this is 1680 kilojoule. So if the engines deliver equal work, the heat input is this much, 1680 kilojoule. Suppose this is Q2, so the first bit is here, if the engines A and B deliver equal work, determine the amount of heat taken in by the engine B. You know, when the two heat engines operating in series are series deliver equal work, that means when WA is equal to WB, we have already we have already proved in the previous question that when work output of two Carnot heat engines operating in series are same, then the intermediate temperature is the arithmetic mean of two extreme temperature, and when the efficiencies are same, the intermediate temperature is the geometric mean of two temperatures. So once we are able to find out the intermediate temperature, we can easily solve questions. So T is equal, if in this case the work output are same, so that's why the intermediate temperature is the arithmetic mean of two temperatures. T is equal to 1000 plus 100 divided by 2. This is equal to 550 Kelvin. 550 Kelvin. So now this is 550 Kelvin. So now Q1 divided by 1000 is equal to Q2 divided by T. So from that 1680 divided by 1000 is equal to Q2 divided by 550. From that Q2 is equal to 1680 multiplied by 550 divided by 1000 is equal to 924 kilojoule. 924 kilojoule. So this was just in the first bit of second part of this question. and that is determine the amount of heat taken in by engine B, and second last bit, the efficiency of engines A and B. So now heat taken in by engine B, that is Q2, taken in by the engine B, or energy rejected by the engine A is same, that is Q2. So Q2 is calculated. Now we are to find out the efficiencies only. This is bit B, answer to bit D and bit E. You know, efficiency of engine A is nothing but 1 minus, since it is a reversible engine, efficiency will be 1 minus sink temperature divided by source temperature. So 1 minus T by 100, T by 100, that is equal to 1 minus 550 by, sorry, 1000, this is 1000. This is equal to 0.45 or 45% efficiency of engine A. Then for engine B, it will be 1 minus 100 by 550, that is equal to 0.8182 is equal to 81.82%. So next question is, you see 6.16. A heat pump is to be used to heat a house in winter and then reversed to cool the house in summer. The interior temperature is to be maintained at 20 degrees Celsius. Heat transfer through the walls and roof is estimated to be 0.525 kilojoule per second per degree temperature difference between the inside and outside. So the room temperature is to always to be maintained at 20 degrees Celsius, and in winter if the outside temperature is 5 degrees Celsius, what is the minimum power required to drive the heat pump? And it can be used as a heat pump in winter, and at the same time it can also be used as a refrigerator in summer season. So but in both cases the inside temperature is to be maintained at 20 degrees Celsius. So first consider the first case. You see, that is the case of a heat pump. So heat pump and refrigerator both are work consuming devices, and they transfer heat from low temperature to high temperature. Suppose the first one is the case of heat pump which operates in winter. This is in winter, the outside temperature is 5 degrees Celsius. In terms of Kelvin, this is 278 Kelvin, and this temperature is to be maintained, that is 293 Kelvin or 20 degrees Celsius, room temperature. So outside temperature is 5 degrees Celsius, and we want to maintain a room temperature at 20 degrees Celsius. And in this case, we have to supply work from outside. Suppose this is the rate of work input, always the rate of work input, and the question is, if the outside temperature in winter is 5 degrees Celsius, what is the minimum power required to drive the heat pump? We have to find out the minimum power required. You see, minimum power means maximum COP. We know that when a heat engine acts in a reversible manner, the maximum work is produced, and when refrigerator or heat pump operates in reversible manner, minimum work is consumed. So for minimum work consumption takes place if the devices operate in a reversible manner and the COP is maximum. And in case of heat engine, when for heat engine there is no COP, only efficiency is there. So when efficiency is maximum, the work production of work or work output of the heat engine is maximum for a given heat input. So here estimated heat loss is given in terms of 0.525 kilojoule per second per degree temperature difference between inside and outside. So यहाँ जो होगा Here it is at temperature 5 degrees Celsius surrounding, and room temperature is 20 degrees Celsius. Obviously heat will flow into this space surrounding, but this is at temperature 20 degrees Celsius, means since heat will flow from this room to the surrounding, so we have to continuously supply some amount of heat so that the temperature would be maintained at this level, otherwise the temperature will go down. So you see, this is the q dot. Q dot is this heat rate of heat input has to be continuously supplied to this room to maintain the temperature at 20 degrees Celsius, and this q dot is rate of heat input is 7 point, this is equal to 0.525 multiplied by 20 minus 5, because in the question it is given that 0.525 kilojoule per second matlab kilowatt per degree temperature difference, but here the temperature difference between the room and surrounding is 20 minus 5, that is 15. So 0.525 into 15, that is equal to 7.875 kilojoule per second or kilo 7.875 kilowatt. This heat has to be supplied to this room to maintain the temperature of the room at this level. So now minimum work COP of heat pump is Q dot by W. Q dot by W dot. This is the rate of power in or power input. So COP. But for minimum work consumption, you see, for minimum work consumption, this heat is constant in this case. This heat has to be supplied. For minimum work consumption, this COP has to be maximum, and COP will be for minimum work input. This is input only. COP will be is maximum. That means 7 point in place of Q dot I can write 7.875 divided by W dot is equal to maximum COP is COP of maximum COP of reversible maximum COP of heat pump is that of COP of reversible heat pump, that is 293 divided by 293 minus 278, that is equal to 19.53. So now W dot is equal to 7.875 divided by 19.53 is equal to 0.403 kilowatt, क्योंकि 7.875 is in terms of kilowatt, or I can express it in terms of watt, that is 403 watt. This is the minimum work input required in winter to maintain the temperature of room at 20 degrees Celsius. So what happens in summer? So what is the maximum outer temperature for which the inside can be maintained at 20 degrees Celsius? What is the maximum outer temperature for which the inside can be maintained at 20 degrees Celsius? So in case of summer, we are required to find out this temperature T. What is the maximum outer temperature? But inside is again in the summer 293 Kelvin. Room is this temperature, but surrounding is at a higher temperature. Obviously heat will flow to this room to increase the temperature of the room. But what the refrigerator has to do is, refrigerator has to same series of devices can operate like a refrigerator in summer. So what the refrigerator has to do is consistently remove heat from this cold space, low temperature area, because the surrounding temperature is at a high temperature, so heat will continuously flow into this space, so that its temperature of this space will increase. But to maintain the temperature of this room at this level, we have to continuously remove heat. So let this heat be Q dot. in case of summer, and work input is W dot. So now the question is, what is the maximum outer temperature for which the inside can be maintained at 20 degrees Celsius, that is room temperature, or 293 Kelvin. But the power input is same as in the bit A. Power input is same, that is W dot is constant at 403 watt. W dot is 403 watt. Now here Q dot is how much? Rate of heat loss, rate of heat transfer, actually heat transfer through the walls and roof में कितना हीट ट्रांसफर होगा? इट इज 0.525 किलोजूल पर सेकेंड पर डिग्री टेम्परेचर डिफरेंस. So that is 0.525 multiplied by T minus 293, because here in this case T is to be found out, W dot is given, this temperature T is to be found out, and rate of heat loss, this Q dot is equal to 0.525 multiplied by T and 293 का difference per degree temperature difference. Here the difference of temperature is T minus 293, and the difference of temperature is same in both the cases in terms of Kelvin or degree Celsius. So 0.525 multiplied by T minus 293, and it is in terms of kilowatt. So this is equal to 525 multiplied by T minus 293 watt. Since W dot is expressed in terms of watt, so I can express Q dot in terms of watt also. So now COP, you see, COP is nothing. COP of refrigerator is desired effect by work input. Whatever heat is removed divided by work input, that is Q dot by W dot, and that is Q dot is 525 multiplied by T minus 293 divided by 403. You see, क्वेश्चन में ये पूछा गया व्हाट कैन बी द मैक्सिमम आउटर टेम्परेचर. You see, from this expression what I can conclude is COP is maximum when T is maximum, because all other things are constant. So COP of this particular refrigerator is maximum when T is maximum. So in the question it is asked that what is the maximum outer temperature, what is the maximum value of temperature T for which the inside can be maintained. So this maximum temperature is possible in case of reversible devices when the COP is the maximum. So when T is maximum means COP is maximum, and COP is maximum in case of a refrigerator working on reverse Carnot cycle, and the maximum COP is equal to 293 divided by T minus 293, and this COP, maximum COP when T is maximum, this equal to this, because when T is the maximum value then COP will be maximum. So equating these two, 525 multiplied by T minus 293 divided by 403 equal to 293 divided by T minus 293. On equating I get T minus 293 square equal to, on cross multiplication, and this is equal to 224.912, or T minus 293 equal to 14.997, or T is equal to 307.997 Kelvin, and this is equal to 34.997 degrees Celsius, or approximately equal to 35 degrees Celsius. So maximum temperature समर में, मैक्सिमम आउटर टेम्परेचर 35 होने तक, ये रूम टेम्परेचर 20 डिग्री सेल्सियस में वी कैन मेंटेन. सो दैट इज द आंसर.